Do you know how to model buckling of columns? Buckling is instability that limits the load carrying capacity of columns. In this tutorial, I will teach you step-by-step process to model buckling of steel columns using ABAQUS. Let us dive into it. Hey friends, if you're new here, I'm Dr. Jawed Qureshi, a senior lecturer at London University. On this channel, we explore life skills to help us lead, examine, and happy life. The problem that I want to model today is SHS, square hollow sections, 100 by 100, and it has been taken from this paper by Meng and Leroy Gardner, and I will attach this paper as well for your reference, and I will attach all the files that I'm going to use here in this model. So its material properties are given here, and its failure load is given here as well, and its imperfection is given here. Now, what does it mean by imperfection? The imperfection that is taken in this paper is it constitutes out of straightness and initial loading eccentricity. So this is the total stiffness, and in the paper they have tried to make it as LCR. LCR is elastic critical length over 1000, and this comes out to be about 1.77. And you will see a step-by-step procedure in terms of how do we model this column. So let us start with ABAQUS. ABAQUS is standard. The first thing, I want to create the model. So I will create two models. One is linear model and other is non-linear model. In linear model, I will carry out the buckling analysis and find out the mode shapes. And after that, I will carry out nonlinear analysis, and it will give me load deflection curve and comparable results with the experiment. So let us say that model is SHS and shell extrusion, and I want to create here a square. So let us say -50 by -50. One corner, another corner is 50 by 50. So you can see that this shape has been created. I will go back again to provide this radius. That is, so the edges are rounded. So this is the outer one, and I will try to extrude the thickness inside, and thickness of the model is 4.02. Although the dimensions are 100 by 100, that's slightly different, but I will assume them to be 100 by 100. So let us see how we can create these. So I will go to this create fillet, and then I will give fillet radius 8.6. That is the outside radius, and which is taken from the paper here. And then click enter, then give the edges, and again give edges here and edges here. And so in that way, I have created the model. Click done, and then give the depth as 1750. Although the depth is slightly different, but to simplify the things, I am giving this length of the column, that is the LCR. So LCR is 1749.8, but roughly I'm saying it's 1750. It's not going to make huge difference. So let us see what other steps we can do. And then I have to define the material. Material is S690. Elastic properties. First, I'm going to run the linear elastic model, and linear elastic model will only use the elastic properties. It will not use the plastic properties, but I will create the plastic properties as well, so that when I copy the model, things are easy for me. Let us do 1,1,0,0, and Poisson's ratio is 0.3, and then I will specify the plastic properties. And plastic properties are here. Plastic properties are 787.3 and 825.8. 787.3. It's not going 787. It is the material. It is the yield. So I'm saying it's 0, and then I'll go back again to specify the ultimate one, which is 825.8. And the strain is given to me 6.02%, which means 0.0062. 825.8, and it's 0.062. Click OK. Once the material is defined, then I will specify the section, shell, homogeneous, and click OK. And here, thickness of shell is 4.02. And I'm keeping everything as it is, the material properties S690. And then I will assign this section to the actual section. Go to section assignment, and then click and then assign this section. Now here I'm going to, shell offset is going to be bottom because I have defined the outer section. Now I want the shell to extrude at the bottom, which means that it will extrude inside the shell. And that means the properties that I have defined, these are outside properties. These are outer properties. Now in that way, section is assigned, and then I will have a look at my steps. So then I have to assemble the model. So let us see how I can assemble the model. Go to assembly, and then instances. Create this instance. Next thing I want to do, I want to define the reference properties. Reference point. So go to tools and then reference point. So the first thing is 0.0,0,0, which is my top reference point, and I'm going to rename this as top T ref. And then I will define the next one, which is the bottom one, bottom reference point. And this is 0,0,1750, which is here. And then I will rename it as B ref. And then I will define these, I will create these sets. And in sets, first I will create the points. So first is top ref. In top ref, continue, I will create this tref point. This will be very useful. I will tell you in a minute why we are creating this. And then bot ref is the bottom reference point. And then I will create the bottom surface and top surface. These surfaces will help me in tying up the reference point with the, not surface, the edges, with the edges. So let us see. Let's see how we can define it. Bot edge. Bot edge is these points. So starting from here, and you have to press the shift button and then choose the property. If you make a mistake, then press control and uncheck it. So you can see that all these edges are chosen here. And then I'll go again back to here at the top. At the top, I can see this surface. When I can see the surface, I will be able to choose it. So again, going to sets, and then I will say top edge. It will help me in tying up the model with the reference point. Starting, pushing down the shift button and then selecting these edges. I made a mistake, and then control. Now, in this way, I have created these top edges as well. Now, the next thing for me is to tie these edges with the reference point. So I will go to constraints, and I will say tie top, and it will be rigid body. Click continue, and then tie nodes. And here I will pick the surface. I'll pick the, for the top one, certainly I will pick the top edge. Click continue, and then for nodes, I will pick the top reference point. Now you can see that nodes here are tied together. And then again, I will repeat the same process for the bottom reference point. So I will say tie bot, and here tie nodes, go to sets. So I want to tie bottom edge with the bottom reference point, go to sets, and then bottom point, and click OK. Now you can see that these edges are tied now. The next step is to define steps and output requests. And then I will define the steps and output requests. So coming here, the step that I want to define is linear buckling. So I will write down linear buckling, linear underscore buckling. And then here it is linear perturbation. And here I will say buckle, click OK. And eigenvalues requested, I want to request 5 eigenvalues, although the only important one will be the first one. And iterations, the maximum allowed are 18, so I will keep it 18. And then I will keep this as 30 so that my analysis does not stop. After defining this, I have to define the boundary conditions and mesh. Let us define boundary conditions. The boundary conditions that I want to define here, these are, so if I go to a step here, initial and boundary condition, the first boundary condition I want to define as pin bot, and pin bot displacement and bottom reference point, highlight in the viewport, click OK. And I want to constrain this in all directions except UR1, except in X direction. It will rotate in X direction, except that it is constrained in all directions. And I want to define another boundary conditions, which is roll top, means roller at the top. And this boundary condition will be the top reference point, click OK. Now here you will constrain everything except loading in U3 direction and X rotation in X direction, because I want to apply loading in U3 direction. So click OK. And boundary conditions are created. Once the boundary conditions are created, I will apply simply a concentrated point load. I will say load top, and load top will give me the top reference, not the bottom one, top reference point. And here I want to define 0, 0, and I will only define 1 Newton to see that how much I'm getting here. And then I will work out the buckling load, and I will apply the same buckling load in nonlinear step. Now, once everything has been defined, the next step is to add this node fill U. This will create a buckling file, and it will create a fill file. And before that, I want to set a working directory, because I want to go all my files in a working directory. So SHS buckling. SHS buckling is my folder, and I will click on that, and I will save my file as well. So it will save everything there. So SHS, I will say SHS model. And click OK. Now it will save everything there in that working directory. Now here I have to define this node fill U. After defining this node fill U, it will actually create a file in which I have all the information about buckling. So click on file, and I will put it in keywords. So if I edit keywords here, and that is before the end step. So before end step, this is my end step. I will simply add this node fill U, and I will tell you what it will do in a minute. And then I think I should have defined a job. I will say linear buckling. Linear buckling, click OK. Now this will create, but before that, I needed to mesh the model as well. So let me go back and mesh the model. Let us mesh the model and see what happens. So seed part, it is saying 88. I will create a 20, apply. And then it had created these points, and then I will go away and mesh the part, mesh part. So my part is meshed. Once everything is done, then I will simply submit this model. And then I will monitor and see what happens. The analysis is completed. It means that my results are fine. And then you can see that the value here is 175516. 175516. So this is my elastic critical buckling load. So I will put this load in a new model. So analysis has been completed. Once it's been completed, then I will go away and click a new model from here. So copy model, and I will say model 2. And click OK. So I have this model 2 now. Now, the first thing I want to do here is that I will go away and remove these keywords. If I don't remove these keywords, it will create a lot of trouble for me. So let's first of all delete those keywords, node fill, because these are related with the linear buckling. The next thing I want to do is I want to remove this step, and I want to create a new step, which is a nonlinear one. So I will say nonlinear buckling. Nonlinear buckling, and this is my RIKS step. Click OK. And here, nonlinear geometry is on incrementation. I will say 1,000 steps. And here I will give 0.001. And because it will apply really very slow increment. And then click OK. Now everything is as it is. Only thing I will apply loading. Now load top. The loading will be equal to top reference point. Click OK. 0 and 0. And now here I will apply loading, which is equal to 1 points, the eigen mode, the elastic critical buckling load. So 1.77516 e raised 6. Click OK. Once this has been done, then the next step is these are steps for nonlinear models. So steps for nonlinear. Also, you have to copy, and then you have to include this imperfection. But this file name, it will bring in the file from the file where you created this. So if I go back again to see where is in here, you can see that it has created linear buckling dot fill. So this is necessary. If it's not created, then it will not patch the buckling mode. Now I'm just interested in first buckling mode, so I will copy this imperfection linear buckling, and 1.77 is LCR over 1,000, or it is the imperfection which is given in the paper, and 1 is the first buckling mode, because I'm interested in first buckling mode. Now let us go back again, and here let us modify the keyword for model 2, and let us put this before the step. Material properties are defined. This is nonlinear buckling. So before nonlinear buckling, I will put these values and click OK. Once it is done, then I will create another job for model 2, and I will say nonlinear buckling. I will keep everything as it is, and I will run a quick data check to see if everything is fine. Node must be a positive integer. Let us see what has happened. Keywords. We just have to give space over here. Let's see. The analysis is completed. All right. I was a bit worried. I mean, something is going to happen, and then anyway, when the analysis is complete, let's go and the analysis is running. It is applying increments slowly, and then you can see that it moved to 0.37. It means that 0.5. It means that 0.5 times the loading, 0.6 times whatever. Now you can see that here it is undergoing some kind of deformation. So that's why you can see these U increments. And now from here, you can see analysis is decreasing the increments, which means that now it is failing. Something is happening over there. So that's the reason it is decreasing the increments. It means that load deflection curve, the load is decreasing. So I will not let it run the entire model. So I will simply kill it here, and then we will see the results. So let's kill the model. Let's see the results. Now here, first thing you want to see the deflected shape. You can see that something is happening over here. You can clearly see that the deflection is happening. If I would have refined the mesh, you could see it even clearly. You could see that this is deflecting. So now I want to plot the load deflection curve. So ODB output and click OK. And then here unique nodal, and here I want to plot the CF point load in 3 direction and top ref. So here the point load is plotted, save, and it has saved the file. And then I want to plot the deflection. Let us see how we can do it. Deflection, and then save. And the next thing I want to do is operate on data. So I will go and click on combine U, CF, and divide it by 1000 to convert it into kilonewtons, and then save as load deflection curve. And here you can see the load deflection curve, and edit. Now here you can see that the load, applied load here is 10 at 5.8 millimeter displacement. I have 1077. And if I go back to the paper, you can see that the load is 1071. So results are really, really close. So it means that ABAQUS can be used to model these columns. But there's a word of caution. I mean, my research has shown that for different lengths, you have to carry out sensitivity analysis for this imperfection. So starting with LCR over 250, LCR over 500, LCR over 1000, and LCR over 2000. So this was LCR over 1000. In this paper, only LCR over 1000 is tried. But for different lengths, sometimes the model does not give you the proper results. So you have to carry out the sensitivity analysis for imperfections. Thank you so much, and I will see you in my next interesting video. Thanks a lot. Bye.